Hello everyone, good evening. Am I audible?
Yes, sir.
Okay, so others will be joining. Do you know anything about them? Harit and
So last class, Harith and Sakib joined.
so we can wait for the 3 4 minutes, then we can start.
Yes, sir.
Okay. Okay, so Sakir has joined. The other one has not joined. Let's say I'm starting, but so he can, meantime, he can join. I'm sharing my screen. Okay, is the screen visible?
Yes, sir.
Okay, so in last class, if I remember, we were doing bond angle questions. So I've given you some rules regarding that one, central atom and side atom. So priority wise, we have to go through. First, we have to see hybridization. If hybridization is same, then we have to see like number of lone pairs. And if number of lone pairs and hybridization both same, then you have to look for central atom or side atom. So rules I have already told you, so I'm not revising rules again. Okay, give me a minute, 1 minute. Okay. Some more question I'm writing. Please try to solve that one. S SO3 I'm writing. In this you have to tell bond angle. Then NH4 plus, NH3, NH2 minus, NH4 plus, NH3, NH2 minus. Then next I'm giving you NH3, PH3, ASH3, SBH3. H2O, H2S, H2SE, H2TE. Okay, I'm giving you 5 minutes. Please try to solve this. Then we will be discussing it. Okay, done.
No, sir.
Okay, so might be you're not able to recall. So let me discuss this one, then next one you can do. So first one, the first way that you have to check out the hybridization. So hybridization, if you check out for SO3, this will be you will be getting sp2, and for this also you will be getting sp2. Okay, so it's simple, like you can take the number of sigma bonds. Here is no lone pair, so Z is equal to 3. So Z3 sp2. Here there is lone pair and two sigma bonds, so Z is equal to 3, you get sp2. So now hybridization came same, so you cannot decide by hybridization. The next is you have to look for lone pair. And I have already told you, lone pair bond pair repulsion is greater than bond pair repulsion. So this lone pair will try to push these two bonds closer by repulsion. So this will give repulsion like this one. Due to this repulsion, this bond will shrink, or you can say the bond angle will be decreased. Here there is no lone pair bond pair repulsion. So that's why only bond pair repulsion. That's why the bond angle will be high in this case. So now next, again the same thing. First find hybridization sp3. Here also sp3, and here also sp3. So basically in NH2 minus, what happens, like there is negative charge and there is also one lone pair already present. So there will be like two pair of electrons with this structure. Okay, so hybridization came same. So now you have to look for lone pair. So here it is zero lone pair. Here it is one lone pair. Here you are having two lone pair. And right now only I have told you that lone pair bond pair repulsion is very high. So repulsion is very high, due to which this bond angle will decrease. They will come closer to each other. In NH4 plus, no lone pair, so no repulsion. So they will have maximum bond angle. And in between NH3, one lone pair. So with one lone pair repulsion. Here, two lone pair repulsion in NH2. So there, the bond angle will be decreased by much more value in NH2 minus. Okay, so this way you will be getting this one. Now, here in this case, so first you have to find hybridization, like I told you. So sp3, 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 sp3. Okay, so this is nitrogen family. If you have seen a periodic table, nitrogen, phosphorus, arsenic, antimony. Now here you can see like hybridization is same, lone pair is also same, because all are having like 5 electrons in their valence shell, 3 used in bonding, the 2 are remaining. So here also one lone pair, here also one lone pair, here also one lone pair, here also one lone pair. So even lone pair also not given you answer. Then the next thing I have told you, you have to look for the change in central atom or side atom. Either of them can be changing. Only one will be changing, not both. Otherwise it will be complex. Here you can see central atom is changing. And in last class I have told you like that one. If central atom electronegativity is higher, so what it will do, it will keep the electron towards itself. So if it is keeping electron towards itself, there will be like more repulsion between the electrons, and it will be opening up more, giving you more bond angle. For example, like if I see here, nitrogen, if I make, so hydrogen, 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 and I'm comparing with this antimony, you can say. Antimony is having much bigger size, so that's why less EN. So here lone pair, the bonded pair are present like this, like this case, very near to nitrogen. And here they will be away from antimony towards hydrogen, you can say. So what will happen if they are towards hydrogen? and they are towards nitrogen. So what happens? More the closer there will be more repulsion. More repulsion, more opening up, more bond angle. That's why your bond angle is directly proportional to En of central atom. So bond angle directly proportional to En of central atom. So you can see here there is more repulsion, there is less repulsion. So that's why nitrogen, phosphorus, arsenic, antimony. So down the group electronegativity decreases. So the order will be like this one. Here you can write En decreases, bond angle decreases. Okay, in next case, first you have to find like hybridization, sp3, sp3, sp3. This is also sp3. Now what will be happening? All hydrogen are same. Then calculate the lone pair. So here you get two lone pair. Here also you get two lone pair, two lone pair, two lone pair. Okay. Now lone pair also came same. Now next what you have to do, you have to see the change in side atom, central atom. So here you can see again the central atom is changing, and period, across the period what happens? En decreases, and I have already told you bond angle will be directly proportional to electronegativity of central atom, because higher En, the central atom will be having holding electron more closer to itself, more repulsion, more opening of bond angle. So same thing like the previous case. So you can write electronegativity down the group decreases, bond angle also decreases. Very easy. Okay. Any doubt in this?
No, sir.
Okay, fine. So let me give next set of question. COF2, COCl2, COBr2, and COI2. So here CO is C double bond O. It will be like this one. Okay. Now again the same step. Okay, don't direct jump the last step. Like in hurry, you can see like the only difference in side or center atom. But go step wise. It will take some time, but it will be like error free. So if you calculate the hybridization, you'll be getting sp3. This also sp3. This is also sp3. So one first step done. Second step lone pair. So here you can easily see zero lone pair. This is also zero lone pair, zero lone pair, zero lone pair. Now comes the third one, that difference in central atom or side atom. So here you can see that central atom is not changing. Central atom is carbon only, but there is difference in side atom. So whenever there is like difference in side atom, so the concept is like that one. For example, I take like this one, C double bond O, F, and if I take like this one, C double bond O, iodine. So fluorine is more electronegative. So here the bonded pair will be more closer to fluorine. And here, since iodine is less electronegative, so the bonded pair will be away from iodine. So you can see here the bonded pair, they are more closer to central atom, they feel more repulsion. So here repulsion will be more. Means side atom is less En, so repulsion will be more because then lone pair will be away from the side atom. So here the bond angle is opposite. Like in the previous case, En of central atom increases, bond angle increases. Here En of side atom increases, your bond angle will decrease. So this you have to remember, it is inversely proportional. So iodine, since having less En down the group, lone pair will be more away from iodine, more closer to central atom, more repulsion, the bond angle will increase. So this will be the final order. Okay, so I have for each rule I have taken one question. So now it is crystal clear. Hybridization, lone pair, central atom, side atom. Central atom directly proportional, side atom inversely proportional. Any doubt in this? Okay. So one question I'm giving to you, you tell me its answer. O lone pair, here hydrogen, hydrogen. O lone pair, here CH3, CH3. Okay. So I'm giving you 3-4 minutes. Please try it and solve it and tell me answer. Okay, done this.
Yes, sir.
Tell what you have done.
So I don't exactly know because like the electronegativities of C and H is like very close to each other. So, but I feel CH3 or CH3 has a larger bond angle because I feel CH3 and CH3 groups, they're like more bulky, so they will have more steric hindrance. Therefore, they will spread out more, and therefore the bond angle will be larger.
Okay, very good. Harit came, then Harit again left. What happened? Saket, can you hear me? Saket? Okay, so let me explain this stepwise. See, according to rules that we have discussed, if you go, we go by that one. So first I have told find the hybridization. So both will be getting sp3. Okay, lone pair, two lone pair. Then comes the number of side atom, central atom. So you can see like central atom is same, but side atom is different, hydrogen and carbon. So electronegativity of carbon is somewhat higher than electronegativity of hydrogen. Okay, carbon will be having more tendency to drift electron toward itself if I compare carbon and hydrogen. And right now we have discussed like bond angle of side atom is inversely proportional to, no, sorry, En of side atom. En of side atom is inversely proportional to bond angle. So if electronegativity carbon is higher, so bond angle of CH3O CH3 should be lower than bond angle of HOH. So this is according to rules whatever we have discussed in hybridization. But like Soham said, this is wrong. Okay. Why? Because here we have to see strict hindrance. Strict hindrance. Strict hindrance means this CH3 groups are bulky. CH3 groups are bulky. So due to their bulky nature, they will be repelling each other. So this repulsion between bulky group, it is termed as steric hindrance. We say like this one. We do not repeat every time that repulsion will be there due to bulky nature. If just we say steric hindrance, it is self-understood that we are talking about repulsion between bulky groups. So more bulky groups, more steric hindrance, the more the bond angle. Their hybridization rules will not follow. Okay, hybridization rule, whatever I have told you, that will be violated. So CSC groups are bulky, more repulsion between bulky groups, more bond angle. So that's why bond angle will be higher of this compound. Any doubt in this? Okay, so likewise, if I give one example, if I take more bulky groups, so here O hydrogen, O CH3, CH3, CH3 C2H5, O C2H5, C2H5. So here you can see C2H5 will be more bulky and they are two in number, so it will be higher. Here one CH3, one C2H5, here two CH3, and here there is hydrogen atom, simple, a smaller atom. So in this way we have to do like this one. Now next topic is Drago's rule. Have you heard this name before? Drago's rule? Hmm?
No, sir.
Okay, fine. Okay, so let me explain this one. So if I take group 15 and group 16, hydride I have to take, okay? Whatever the element present in group 15, group 16, their hydride I have to talk about. So this will be like NH3, PH3, ASH3, antimony NH3. Okay. So what is happening? The bond angle that is observed for NH3, it is coming like 107 degree. So that is justifiable. Like if you take the hybridization, you will get sp3 tetrahedral 109 degree. Technically, it should have, but lone pair is there, so some repulsion. The bond angle will shrink down. So 107 degree it is coming. It is acceptable. But from phosphorus till antimony, the value is very much near to 90 degree. Here you will have 93 degree. Here you have again 92 degree. Here you have 91 degree. So the values are very much close to 90 degree. Now what is happening? Why this is happening? The reason for that one is that if you collectively see this third period onwards, here the central atom is not involved in hybridization. Okay. So if hybridization it is not involved, hybridization will not be sp3. Here the bond will be made with pure p orbitals. Pure p orbitals. Okay. Now how pure p orbitals look like? They will be having perfect like x axis, y axis, and z axis. And there, like you can see, it is px, py. Sorry, this will be pz. This will be py. This will be pz. So they are all having 90 degree. So of course, if pure p orbitals is involved in making bonding, so hydrogen will have s orbital here. So the bond angle will be closer to 90 degree. So this you have to remember. This is Drago's rule. Okay. So okay. So if I tell in the form of orbital, so nitrogen, you know it is 7 atomic number. So 1s2, 2s2, 2p3. So 2s and here 3 single electron, 2p. What is happening? Hybridization will happen, and then you will get 4 sp3, and they will make bond with 1s. So let me make this properly. So here you can see it is making bond with 1s. This is also making with bond with 1s. So here you will be getting 4sp3 1s bonds. Okay. So here you got sp3 1s bond. That's why tetrahedral. So by easily you are getting 107 degree closer to 109 degree. But if I talk about here phosphorus is 15, 1s2, 2s2, 2p6, 3s2, 3p3. Okay, so this is your 3s, this is your 3p. Ds and 3p, and this is like px, py, pz. So here hybridization will not happen directly. They will make bond with directly. They are going to make bond with 1s. Okay, so here you will be getting like so this orbital is 3p and this is 1s. So here bonds you will get 3px 1s, 3py 1s, 3pz 1s. Here you can write sp3 hybridization of NH3. That's why bond angle closer to 109 degree, 109 degree 5 minutes. Okay, so that's why for nitrogen it will be like closer to 109 degree. The rest other three after nitrogen, third period onwards, they will always have closer to 90 degree because hybridization does not happen. The pure p orbital that is present in outermost shell, they will take part in hybridization. Okay, any doubt in this?
No, sir.
Okay, so now we have to see like its application, how it is being applied. So suppose if I take NH3, so NH3 and ES3. Here you will be having lone pair. Here you will be having lone pair. So first you have to like apply Drago rule and you have to check for hybridization. So here it will be sp3, but for phosphorus you cannot write sp3. Okay, so percentage S character if I talk about here it will be 25%. Here percentage S character will be 0. So since percentage S character is 25%, So we have to see like which one is good in terms of basicity. So if we talk about good base, so good base are those base which donates lone pair very easily. Okay. So if I say like that one, so you can write here which donate lone pairs easily. And if I talk about S subshell, they are more closer to nucleus. If percentage S increases, it attracts more lone pair towards itself. Lone pair lone pair will be difficult to donate. And if we talk about lone pair, so lone pair itself, they are having percentage S character. If you remember in last class for trigonal bipyramidal, I have told you like lone pair occupy the position which are having more electronegative atoms, like out of equatorial and axial. I've given equatorial is sp2, axial is pd. So equatorial sp2 more percentage character. So lone pair will be more attracted towards sp2 due to more electronegativity. So once lone pair goes to that sp2 position, they will have more electronegativity. So this also you have to remember. Lone pair always have slightly more electronegativity. Okay, so sp3 according to normal rule, but that sp3 is also varying between hydrogen and lone pair, because like stick number we got 4 because of 3 hydrogen and 1 lone pair. They are alike, hydrogen and lone pair are alike. Now that sp3 will be further divided differently between hydrogen and lone pair. Lone pair technically it should be sp3 only, but it will have more than like sp3, so 25% should be the S percentage. But since lone pair it is, so it will be having much more than 25%. Okay. And hydrogen sp3, since some part of percentage is given to lone pair, so hydrogen percentage S character will decrease. So that will become like 25 to 23 or 22 like that. So even sp3 also vary between lone pair and atoms. So this you have to remember. So if I talk about like pH3, so they all are having perfect 90 degree, 90 degree, 90 degree. And lone pair, if I talk about phosphorus, so phosphorus percentage S is 0. Lone pair is not linked with phosphorus orbital. It will be separately. So here you can see like technically the lone pair is having is only occupied in S subshell. If you can see like in here, if I have written the phosphorus electronic configuration, so your lone pair is only residing in S subshell. So here we are talking about lone pair. So percentage S should be like 100% here. 0% I have written with respect to hybridization. The hybridization is not happening. With respect to phosphorus, you can say. So phosphorus only p orbital, the bonding that is taking place between only p electrons. So the bond is formed between only p. So bonded pair of electron, percentage S is 0. But since I've given you the entire concept of lone pair, so we are only concerned here with lone pair. So this is percentage S of lone pair. So this lone pair is sitting inside the S subshell. So percentage character 100%. Here lone pair is sitting inside the sp3. So percentage character 25%. So I have given you entire story. The one which donate lone pair easily, that is good base. So can you tell me out of this NH3 and PH3, which one is good base? You understood this or not, or may I explain once again?
Sir, I did not get it.
You didn't get it. Okay, I'm explaining once again. Drago rule you understood.
Yes, sir.
That nitrogen will have sp3, phosphorus will not have hybridization.
So pH3 is a good base because no, NaC is a good base because it has only S character 25%, and PHC is not such a good base because it is S character 100%.
Yeah, I told you that lone pair sitting at a place, what percentage character it is having. That will decide whether it will be donated easily or not. So percentage character is less. So lone pair can come out easily out of nitrogen, but phosphorus it is sitting inside the S subshell only. That is 100% S character. So that won't let come out easily. Understood? So you're right. NH3 is good base, and it is poor base or weak base. So may I explain this again? The other two you tell, Amitesh and Saket. Okay, once again I'm explaining. It is a bit tricky. See, basicity depends upon only like donation of lone pair. If atom is able to donate lone pair very easily, it is good base. If it is unable to donate lone pair, it is weak base. Now we have to see lone pair, where lone pair is sitting. Percentage S is more, it will be more electronegative position that will not let lone pair go out. If percentage S is less, it is very easy lone pair to go out. Now, since I have taught you Drago rule, hybridization does not take place phosphorus and onwards. So if you write electronic configuration of phosphorus like this, you can see the lone pair is sitting inside the S subshell only. Hybridization does not take place. So S subshell percentage character will be 100%. So that will be very electronegative position. So that will not make lone pair come out easily. But in nitrogen, hybridization happens. sp3 hybrid orbitals are formed by intermixing. Then sp3 will be having lone pair. So percentage character is only 25%. 25% will be less electronegative. So lone pair can come out very easily. So it's good base. Then I told this last point that if I consider only sp3 and sp3 like this one. So in the previous case, like I've drawn, you can see 4 hybrid orbitals are there: sp3, 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 sp3. So this further have some difference. The lone pair containing sp3 will be having more percentages character because it is having lone pair. Okay, so that will I will tell again. So no need to mix up here. Just like that only I put. So its application can be seen like this one. If I write reaction between NH3 plus HCl, so acid base reaction. So this is good base. Okay. So this lone pair will be easily donated to this hydrogen, and you will get compound NH4Cl. If I take PH3, here also lone pair is there, and HCl. Here, since it is weak base, reaction not taking place. Okay. So likewise, if I take NH3, NH2O. So again, here it is good base. It can donate lone pair easily to hydrogen. You get NH4OH. Now if I take PH3, it is also having lone pair since, but it is weak base. The reaction with H2O, reaction not taking place. Okay, understood this? Any doubt?
No, sir.
Okay. So this whatever I have told you, group 15 I have told you. So in group 16 also it will be applied. So group 16 you have to take like this one, H2O, H2S, H2SE, H2T. So here also like second period, hybridization happens. Okay, hybridization happens, sp3. The bond angle it is coming like 105 degrees, so closer to 109 degree. Because there are two lone pairs, no? So two lone pairs will give more repulsion, so that's why it closed down more. So this is like bent shape. I pulled bent shape. It is V shape, bent shape. That's why it is 105 degree. But if I consider all these three, so they will be having like 93 degree, 92 degree, 91 degree like this one. Here it is no hybridization, pure p orbital participate. Okay, so this I told in last slide. Px, Py, Pz, they are participating. So pure p orbital participate. Okay. So now next topic is Bend's rule. However, I have discussed this with you all, and I've also told this one. But once again, I am telling this to write down because it is important. So you can write down when all surrounding atom attached with central atom through single bond, then more En atom, then more En surrounding atom prefer to attach that hybridization orbital which is having less percentage S character. So this is regarding that TBP geometry, equatorial and axial plane that we have discussed in last class. That is only I am telling. There I told you equatorial and axial, more electronegative atom will go at axial because that is having less percentage S character. And lone pair go to equatorial because that is having more percentage S character. Higher percentage character, that is equatorial, and higher En will repel each other. Okay, so first let write, then I will explain this. Here you can write more En will go to less percentages position. Okay. Now second point, lone pair and multiple bond prefer to stay with that hybrid orbitals which has more percentage S character. So two rules I have told you. One is regarding more En and one is regarding lone pair. Okay. More En atom will go less percentage S character position. Lone pair will go to more percentage S character. So it is logical also. Lone pair are the electrons. Electrons coming. So the position with high percentage character that will have higher En. So that higher En will attract lone pair. So lone pair will go at higher percentage character. Now more electronegative atom, like for example fluorine. So fluorine, if it is going to higher percentage character, that will repel each other. Because fluorine also higher En, higher percentage character position is also higher En, so they will repel each other. So fluorine will go to the position which is having less percentage character, so that will be less En. That's why less En and more En is going there, so they will neutralize each other. So this we can understand by this diagram. So if I am having compound PF3Cl2, okay, so hybridization will be like sp3d. So TBP geometry, Sb3 TBP, phosphorus will be central atom. This is equatorial position and this is axial position. This I have already told you, this is sp2, 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 and this is pd. This is also pd. This is known as equatorial. This is known as axial. This is like 120 degree. Okay. So now you can easily see which one is having percentage S higher. So here in equatorial, percentage S is higher in equatorial. So fluorine AN is higher than fluorine EN. So what I told you, fluorine higher En atom will go to the position with less percentage S character. So that's why your axial PD position, here fluorine will be going. Here fluorine. And the chlorine less En will go to higher percentage S character or higher percentage hydrogen position. So hydrogen we are having equatorial. So here chlorine, here chlorine. Now one fluorine is left. There is no position in PD left. So it has to go in equatorial only. So in last class also we have done this one. So once again I have told you, because this is very important in class 11. If you know this beforehand, that will be like an advantage to you, because there this much time it is not there that it has to be explained properly in class. So likewise, if lone pair is there, so lone pair will be going in higher percentage position. So this you have to remember that high percentage S means high En. Okay. So any doubt in this? Ask if you are having any doubt.
No, sir.
Mitesh, can you hear me? Harit, your mic is not working. Okay, fine if it is not working. Okay, so last week notes I forgot to share. So today I will share the last week notes also and today's notes also. Okay, so you can revise, and if you have any doubt, you can ask me in next class. So today I will try to complete this chapter, chemical bonding. Next week we'll be starting new chapter. Okay, so let me move ahead. Okay, so now bond angle we have done multiple aspect. Next property is bond length. Okay, so bond length is basically internuclear distance. So two atoms, suppose they are closely connected like this one. So between, if I see the line, the distance between their nucleus, that will be like bond length. And bond order, we have already discussed. First of all, bond order is like the number of bonds. If you are having simple molecule, suppose H single bond H, so bond order will be 1. If you are having O double bond O, so bond order will be 2. Okay, but if you are having resonating structure where you are not getting perfect single bond double bond, so there I have told the formula. Suppose you are having this one, so there you apply bond order 1 plus pi upon sigma, 1 plus number of pi bonds divided by number of sigma bonds. So from there you'll be getting bond order. So now bond length, how, like I have given the different priority order for bond angle. Look, first look for hybridization, then lone pair, then you have to look for central atom, side atom. So here also you have to perform like that one. Okay, so let me draw the chart. So four compounds will be given to you, and they will be asking bond length. So you have to compare. There will be some difference in atoms. Then only you can compare bond length. So first you have to do comparison of atoms. Comparing atoms. So if you compare atoms, so they can be of same period or different period. Okay, same period. For example, carbon, nitrogen, oxygen, fluorine, same period. But they can be of different period also. Fluorine, chlorine, bromine, iodine across the group. So if they are different period, your work is very easy because you know on switching from one period to next period, number of shells increases. Number of shells increases, your internuclear distance will increase. One atom will be very big, so your bond length is very high. Okay, so it will be like this one. Suppose if I take HF, HCl, HBr, HI, it will be like this one. Cell size increases, bond length increases in this way. But the question will be not asked on this way because complex question cannot be made on this concept. It is very easy, not so tough. But same period again, then you have to look for bond order. Okay, same period, then you have to look for bond order. There can be like single, triple, double bond. You can easily see bond order. Bond order is higher, so it will be like double bond or triple bond, so bond length will become shorter. But here also, like bond order, if you talk about, bond order can be same also, and bond order can be different also. If it is different, then it is fine because bond order increases, bond length decreases. So bond length will be 1 upon bond order. But if bond order is same, then what? Okay, you are getting same bond order. Then on the basis of bond order, you cannot say which one is having higher bond length or lower bond length. Same. Now here also like bond order is same. Then you have to look for the atoms which are different. Okay. If atoms are different, atoms are different, so their size will be different. If different atoms are different, so size will be different, and if size increases, bond length increases. Okay, atoms are different. If size increases, bond length increases. But what if bond order is same and your atom is also same? Then your hybridization or the percentage S character will be changing because there will be like difference in lone pair electronegativity like this one. From that you have to quickly sense for percentage S character. If percentage S character will be increasing, means more electronegative, more tendency to attract electron towards itself, your bond length will become short. If percentage S character is decreasing, means it is not attracting lone pair very uh, very powerful, you can say, with more power. So your lone pair will be away, your electron will be away from the atom, so your bond length will become longer. Oh, so because I have written wrong. Here bond length will decrease. With more electronegativity, bond length will decrease. With less percentage character, it will not attract electron, so your bond length will be higher. More attraction, the bond length will shrink. No attraction, less attraction, the bond length will be higher. So this much work you have to do to see the bond length comparison. Any doubt in this? We'll be solving some questions that it will be more clear. But first say if you are having any doubt. Hmm?
I've seen.
Okay, so let me take some example, then it will be more clear. So suppose first one I have taken H2O, H2S, H2Se, H2Te. So first you have to see across the same period or across a different period. So you can see it is across the group, different periods, cell size increase, the bond length will increase, very easy. So sizes you have to see here, cell size that is increasing. So next example I have taken C2H2, C2H4, C2H6. Now same period, but if I make its structure, it will be like this one: HC, triple bond CH, C double bond C, hydrogen here, hydrogen here. So it is also very simple. Bond order here is coming different. So quickly you can write here bond order 3, bond order 2, bond order 1. So I told bond length is inversely proportional to bond order, or you can see like triple bond will be shorter than single bond and double bond. So the order came like this one. It was also very easy. Now you have to see carbon hydrogen bond length in this compound. CH3 plus, CH3 minus, and CH4. So here, see, they are same period. Bond order will be also same. Single bond will be there. No resonance, so you cannot apply 1 plus 5 upon sigma. Atoms is also same. The atoms are not different, they are same. So the only left in this chart, the way through which you can define bond length is percentage S character. Other are not working. Okay, because bond order is same. Bond order is same and the atoms are not different. So you cannot look for size. Carbon, carbon, carbon is there. So here only you can see like percentage S character. So for percentage S character, it will be like sp2. This will be sp3. This will be sp3. So what I told you, percentage S character increases, more tendency to attract electron, the bond length decreases. So here you can see 33%, here 30, here 25%, 25%. So I will be telling this sp3 how to see between them. But sp2 percentage S character is higher, so bond length will be shorter. So anyway, this CH3 plus will be the lesser one. Now between CH3 minus and CH4 we have to see. Here see how to see. Okay, let me explain next slide then and we will let you know. See if I draw CH3 minus. So minus means one lone pair will be there, like this one, hydrogen, hydrogen, hydrogen. And CH4 will be like this one, H, 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 H. Now for lone pair, what I have told you, the lone pair reside in the position where percentage character is higher because they need some higher En position. So higher En will attract lone pair, higher En percentage character. So here what you have to do, both are having sp3, both are having 4 sp3 hybrid orbitals, but between that 4 sp3 hybrid orbital also there is difference in variation of percentage character. It is not 25% in each case. For lone pair, percentage S character will increase because it is going in the position where percentage character is more. So if lone pair, see, total the mixing is 4 times sp3. If one of the orbital is having more percentage s character, the other orbital will have to compensate that one. So that's why for other, here percentage s will decrease. So here the carbon which is having sp3 here, in that sp3 of the bond made, percentage s will decrease. Here also percentage s will decrease of carbon hydrogen. If percentage s character decreased of carbon hydrogen, so En of carbon is decreased in the carbon hydrogen bond, so your bond length will become longer. So that's why this lone pair one carbon will have longer bond length than this one. Here all will have similar sp3. Here the sp3 will be the bond of carbon hydrogen. That sp3 will be less in percentage s character. So that's why the bond length is becoming greater. Understood this one, or may I explain this again? So internally, now we have to see percentage S variation. Here I am talking about percentage S of carbon within, you can write like this one, within 4sp3 hybrid orbital. Within 4sp3 hybrid orbitals. Okay, one more example I am taking, then it will be more clear. CHF3, CH2F2, CH3F, and CH4. So here also, if I go by flow chart, they are same period, bond order is same, all single bond. The atoms is also like there is no difference. All the atoms are same. If all the atoms are same, percentage S you have to see here. Now here what is varying? The number of fluorine atoms. Now the orbital in which fluorine bond is made, carbon fluorine, here percentage S character will decrease because higher electronegative atom goes to position with less electronegative atom, with less electronegative, because Morian will repel each other. So if fluorine is going to a place or the orbital where it is less electronegative, so its percentage S will be low. So all the 4 bond will have 4sp3. If on some of the bond percentage S is decreasing, so for other carbon hydrogen, bond percentage S will increase. So more percentage S character, the bond will become shorter. Here also you can see like carbon fluorine orbital, percentage S will be like increased, but to lesser extent, because there are 2 fluorine atoms. So carbon hydrogen orbital, percentage S will decrease to a smaller extent. That's why they will be having some sort of attraction of electron, but the bond length will be shorter of CHF3 because their percentage S is higher. So attracted more. 1 minute, I have written opposite. carbon, fluorine. Fluorine will go to the position with less percentage S character. So decrease will be less, increase will be also less. However, there will be some increase, but increase is less. That's why bond length will be higher. CH3F, CF orbital. Here percentage S character, since there is only one fluorine atom, so the degrees will be very less. So CH orbital, here percentage S character will be also increased by less extent. Here it is increased by larger extent. So the bond length will be higher for CH3F. Now CH4, it is easy. There is no fluorine atom. So there is no fluorine atom. So this hydrogen will have like proportion in proportion of sp3. So percentage S will be less than that of CH3F. So that's why it will be having maximum bond length. Understood this or not? Or may I explain this again? Soham?
Yes, understood.
Okay, then tell me the next one. Let you do next one. CHF3 and CHCl3. CHF3, CHCl3. Okay, so I'm giving you 3-4 minutes. Please do this one. Okay, take one more. C2H6, E2H4. No, this we have done already. Leave this one. Okay, do this one only. So I will be discussing this again. Okay, done.
Yes.
How you have done?
So F is more alternative than C. So CF has more S character than CL. CCL, CF has more character than CCL. So so the CH bond in C in the first compound has less S character than the CH bond is in second compound. So therefore the bond length in CHF3, the CH bond length is more than that in CHCH3.
See, in the previous case, if electronegative atom I am taking, so percentage S is less or high. Hmm? I,
It's less.
I think you have done opposite.
Yes.
See, whatever you have done with respect to lone pair. For lone pair means if you are getting lone pair, number of lone pairs increases, so percentage S character will increase of that orbital because lone pair goes to position where electronegativity is high. But higher En atom will go to that position where En is less because high En will repel each other. No? Like what you have done carbon fluorine is having higher percentage S character. This you have done, no?
Yes.
Carbon fluorine will have less percentage character because the percentage character we are talking about is it is of orbital in which atom is going to take position. If you will take higher percentage character, so fluorine will repel from that position. So fluorine will go to the position which is having less percentage character. Understood?
Yes.
So whatever you got, that opposite will be coming. Otherwise, you have done right. So carbon fluorine orbital percentage S will decrease very rapidly because more En goes to less En, or you can say less percentage S position. So your carbon hydrogen percentage S will increase very high. Here carbon chlorine orbital, since chlorine is less En than fluorine, so percentage S will decrease by lesser extent. So your carbon hydrogen percentage S will increase by lesser extent. It is more increasing more extent, so more percentage S, the bond will shorter and your bond length will decrease. So in this way. Okay, next I'm going to take O2, O3, Na2O2, and H2O. Okay. So whenever this type of compounds are coming, no, so it's better you draw its structure. I already told you how to draw a structure. It can be resonating structure or simple structure. You draw a structure. So O double bond O, like this one. Here resonance will be there. O double bond O. Formal charge you placed, so you will get this structure. Then Na2O2. See Na2O2, that will be like Na means two oxygen atom bonded with sodium and sodium. So you can break that bond between oxygen and sodium. So Na plus will form and O minus will form. So basically you are having here O2 2 minus and minus charge is lone pair. So here O single bond O, and since minus charge is there, already there were two lone pairs in oxygen. So after negative charge you will have three lone pair. And this is, it is H2O2, O single bond O, here hydrogen, here hydrogen. So here you will be having two lone pair. Now you have to see. So now these atoms are of different group, different period, or you can say like since all are having oxygen, so same period. Then comes bond order. So bond order you have to see same or different. So bond order for these two compounds it will be same Na2O2 and H2O2 because single bond is there. For these two compound bond order will be different. So here double bond, so bond order will be 2. Here bond order it will be 1 plus pi upon sigma. So pi here is 1, sigma are 2. So you are getting 3 by 2. Now I told bond order is inversely proportional to bond length. So O2 will be shorter than O3. First we got this one. Now between this H2O2 and N2O2, the difference is only of lone pair. Okay. So lone pair orbital percentage S character will increase. Okay, because lone pair will be taking the position where is more En, so more percentages. So O single bond O orbital, here percentage S character that will decrease. Okay. Likewise here also, since there are two lone pairs, so lone pair orbital percentage S will increase by lesser extent, but O single bond O orbital percentage S will decrease by decrease by shorter extent. So that's why Na2O2 will be greater than H2O2. Now, since single bond is present in Na2O2 and H2O2, so in any way Na2O2 and H2O2 both are greater than O2 and O3. So collectively you can write like this one. The highest bond length will be of Na2O2. Okay, here you have seen the percentage is decreased by very large amount, so it became more bigger. And these two are greater than these two because bond order here is 1 1, here 3 by 2, here 2. So 2 bond order least, 3 by 2 in between, and these two are 1 1. So this understood, this I have taken example with lone pair. So previously electronegative atom percentage character decreased, here lone pair percentage character increased. So any doubt in this?
No, sir.
Okay, so next is if I take this NO2 plus, NO2 minus, and this is NO3 minus. Okay, so if I draw its structure, it will be like this one. It is linear. Bond order you are getting 2. Then you are having this one. So N double bond O, single bond O minus. So here you can see resonance is there. So bond order will become 1 plus pi upon sigma. That is 1 plus pi is 1, sigma is 2. So 3 by 2 you will getting. So you will get 3 by 2. Now here you can write N plus So bond order you can find simply here. 1 plus pi upon sigma. So pi is 1. Sigma is 3. You are getting 4 by 3. So based on this value, the higher bond order, the shorter bond length. So NO2 plus will be the shorter. Lower bond order, longer bond length. This you are getting shorter one. So NO3 minus, then NO2 minus, then NO2 plus. Any doubt in this? Hmm?
No.
Okay. So this type of question also coming. This compound we have taken of TBP. So always, okay. So here in equatorial, so this is C bond length between P and Cl. Between phosphorus and fluorine, it is B bond length, and this P fluorine of equatorial, that is A. Now here you have to find like the order of A, B, C. So here we have to do question with bond angle, okay? Because the bond angle will be different. If I see like here bond angle, it is 90 degree, and here it is 120 degree. So with bond angle also, you can check the difference for difference in electronegativity. So if bond angle is higher, central atom has higher electronegativity, more tendency to attract more percentage as character. Okay, so like I told you, bond angle is higher, means central atom En is higher, means here reverse I am doing. So in for bond angle, the rules which I have given for central atom, if En is higher, bond angle is higher. I told this one. For side atom, bond angle is inversely related to En. For central atom, bond angle is directly proportional to En. So if bond angle is higher, your En is higher of central atom. If En is higher, so percentage S character will be higher. So here you can see like if I compare with axial bond length with equatorial bond length between A and C. So for C, you can see it is 90 degree. So less bond angle, less percentage S character. For 120 degree, higher bond angle, more En, more percentage S character. So that's why 120 degree bond length will be shorter. So C will be greater than A. You can write here more bond angle, more En of central atom, more percentage S bond length decreases. Okay. Now if I see between CBA, so C you are having with chlorine, and B and A equatorial and axial. So in any way between B and A, B will be higher one because bond angle is lower for B. So same here, B is greater than A. A will be shorter because A is having higher bond angle, higher percentage characters, bond length is same. Now between C and B, how to do? Now between C and B, you can see chlorine and chlorine. So fluorine higher En, so percentage S will decrease to larger extent. And for chlorine, percentage S will decrease to lower extent because En is higher. En is lower, sorry. So percentage S decrease to lesser extent for chlorine. So fluorine bond will be higher. Move on here. Okay, so see here, this is percentage S of chlorine. Okay, percentage S of chlorine. So higher En goes to place where percentage S is less. If I talk about percentage S of phosphorus, if fluorine it is decreased, for phosphorus it will be increased. Here also percentage S of phosphorus because through central atom we are seeing. No? So you can see for phosphorus here it is raised by extra extent. So the bond length between B and C, B will be shorter. So you'll be get like this one, CBA. Okay, so you can watch recording and see the notes once again. Maybe in one time you will not be getting it. But if you do again, you will be getting it. So next compound is IF7. Okay, so here like the geometry will be like this one. I bonded to 5 fluorine atom in one plane, like this one. Pentagonal pyramidal, that will be geometry. Pentagonal bipyramidal. And the 2 fluorine atom are lying above and below the plane. So here also bond angle is changing. You can see here bond angle you are getting 72 degree. And here with above and downward fluorine you are getting 90 degree. So again the same concept. If I give the nomenclature to this equatorial bond length, that is B, and the axial bond length, that is A. Okay. So you can see like higher bond angle, more En, more percentage as character. So bond length will be shorter. So that's why B is greater than A. Because you can write reason here. 90 degree bond angle is higher, percentage S character is higher, En is higher, bond length decreases. Okay. Next one. If I give compound BRF, so bromine has 7 unpaired electron. Sorry, 7 electron in its outermost shell. So 1 electron used for bonding. So 6 electrons are remaining, so that they will be forming lone pair. So hybridization will be coming like BRF2. It is sorry, BRF2. Take this as BRF3. Sorry, BRF3. So if you take the hybridization, it is like two lone pair and three bond pair. So this will be sp3d. So again, trigonal bipyramidal geometry, sp3d, pbp geometry. But here, when you draw its structure, bromine will be having three fluorine and two lone pair. Lone pair will be always going to equatorial position because that is having high percentage S character. So lone pair will be given in equatorial and one equatorial position left, that will go with fluorine. Here also fluorine, here also fluorine. So it will look like this one. Now if I say A and B, if I'm taking this as B and this is A. Now here again, the equatorial bond angle, that will be like 120 degree and this will be like 90 degree. So higher bond angle, more percentage character, shorter bond length. So here you will be getting A greater than B, because in A you are having 90 degree. Bond angle is lower. En will be En of central atom, that will be lower. So your bond length will increase. Okay, so last one. After this, your chapter will be over. Three compounds are given: P, Cl, Cl, here Cl, here you are having F and F. Then you are having PCl, Cl, here F, here F, here F. Then you are having PCl, sorry, here ClF, here F. Here you are having F, here you are having F. Now, here you have to tell order of bond length of PCl. Okay, so PCl bond length you have to say. So now you can compare, like here there is zero fluorine atom in equatorial. Here one fluorine in equatorial. Here one fluorine in equatorial. Or collectively also you can take, no issue. See, here two fluorine, three fluorine, four fluorine. So when electronegative atom increases, percentage S character decreases because higher En will try to take that place where En is less. Percentage S is less. So here percentage S of fluorine will be decreasing very rapidly. Percentage S of F will decrease very rapidly. Here percentage S of F will decrease somewhat less, but here percentage S of F will be even decreased by less. So if F is decreased, Okay, so if F is decreased, so for chlorine, it will increase also very rapidly. And here also, percentage S of chlorine increased by 3 arrow. Here, percentage S of chlorine increased by 2 arrow. So easily you can see here increased by larger extent. So carbon chlorine bond will be shorter here, and here increased by somewhat lesser extent. So bond length will be higher in this case. Okay, so your chapter is over. You can watch the recording and you can see the notes. I will post the notes in group. If you have any doubt in next class, I will be clearing it. You want to say something? Or you are having doubt present also, I can discuss if you want to tell. Hmm? Well, you are having doubt? Or we can wrap up. Okay, fine.
Yes.
Okay, fine. We will be wrapping up. You can watch the recording in notes. Then we can discuss notes, doubts in next class if you are having. Otherwise, I have taught in depth and I have also repeated multiple times, so I don't think doubt should be coming. But in any way you are having doubt, I will be discussing it. Okay. So we are wrapping up. Thank you.
Thank you so much.
Thank you so much.